So hello and welcome students to the course MA412 linear algebra, and today I think this is lecture number 12. Lecture number 12. Okay. In today's lecture we will learn a very important idea. And we will learn few new things. So there's something called eigenvalues and eigenvectors. Okay. Yeah, in some books they also call characteristics values and characteristic vectors. So I can write down both the names. So I also call characteristics. Okay. Characteristic value and characteristics vectors. Okay, so both the terminology are same. Okay. So let us define it. What does that mean? What do you mean by characteristics value or the vector vector? So let me start with a definition. Okay, so let E be a linear space or some field. So linear space over some field F. Okay, and you have a linear operator T, which is the element of LV. Okay, then we defined so in non-zero scalar sorry, I should not say non-zero. A scalar, maybe I should say scalar. Say C belongs to F is called a eigenvalue is called the eigenvalue or an eigenvalue. Also you can call characteristic value. Okay, it's called eigenvalue of T over F. So why I'm saying over F, because F is very important. If we change the F, then the eigenvalue may change, or it can be the case that eigenvalue may not exist for some field but may exist in another field. Okay, that's why this field is important. So a scalar C is called an eigenvalues of T over F if there exists a so here I need non-zero one. So non-zero vector V is the element of V. Okay, such that what happens? So T of this V is the image of V under T is nothing but the sum multiple that C multiple of V. Okay. So what geometrically what does that mean? So that means that you have an original vector, say for example V, and when you apply T, and then the image will be on the same so you know that any line passing through so this origin is it's a vector space, the surface of that original space. So this will be the same subspace, and not only that, it can be multiplied by C. So you have original B, now it is CV. So CV is what? This is nothing but image of V under T. So this is the meaning of geometrically, the meaning of eigenvector, and eigenvalues are that C, that multiplication. It can be 0 also, no problem. It can be the case that it image is mapping to the 0 vector also. Okay. And in this case, this non-zero v is called an eigenvalue, eigenvector of t over f over the field f. Okay, and okay, so this is clear. So if you start with a linear operator on V and you check. So this definition is more general. I did not assume any dimension, anything. Okay. Now for finite dimensional, you have much more thing happen. Actually, there are equivalent conditions for finite dimensional. But in general, if the dimension of the vector space is not known, it may be finite or infinite, you can define by this. Okay. So you find out, so an element is called eigenvalues or characteristic values if there exists an eigenvector, which is actually non-zero vector, satisfying this condition that TV equal to CV. Okay, then we call C is an eigenvalue and V is an eigenvector corresponding to the eigenvalue C. Okay, it may be the case that for a particular T there might be more than one such C, like there might be more than one such C which satisfy this kind of condition. Okay. So that means there might be more than one kind characteristics values or eigenvalues of a linear operator. Okay, I will give some example. Maybe we can start with some basic example. Okay. For example, what about this known linear operator that we already learned as an identity operator? Okay, so these are all simple example. So you have identity from V to V. Okay, the identity sends every element V to V. So this is by definition is clear that the one is the eigenvalue, right? So here one is the actually you can show that the eigenvalues the only one is the eigenvalue. It can repeat obviously. Okay. So by the way, in the definition also I did not say that characteristics value or eigenvalue will not repeat. It can repeat also. C can come more than one times. So one is the eigenvalue. Okay. Similarly, for zero operators, you know that the zero is the eigenvalue, right? It's obvious. And now, what happens if you there was another operator we discussed something called rotation, right? You remember rotation by some angle, right? You have something and then you rotate it anti-clockwise, something, so theta. Now if you give this rotation, then what happens? For example, suppose you are giving rotation, actually theta is say pi by 2. For theta pi by 2, what happens? So you start with the vectors, and if you give rotation, so this is V, and if you rotation, so TV will be what? TV will be this vector, right? And this, certainly this is not some multiple of C and V, right? Because this will, whatever the vector you choose, if you give rotation by 90 degree, it will never lie on the line. This, okay? So this is never this C for any C belongs to F, right? But if you give rotation by pi, that means 180 degree, then it will come here, right? What does that mean? That means this is kind of negative of such vectors, right? In that case, negative of 1. So for theta equal to pi, you can see that TV equal to minus V, right? So in that case, C equal to minus 1, right? Okay. So it depends on for which vectors what is the angle you are rotating for which whether t has a eigenvalues or not. So in this case it doesn't have eigenvalues or eigenvector when theta equals pi by 2. For pi you can have eigenvalues -1, eigenvector any non-zero vector is eigenvector, right, with respect to -1. Okay, so maybe let me discuss few more examples, then you will have. So you recall that we define this space of functions, right? So there is a very special subspace. So maybe we recall that space of functions, say from say R to R. Okay, space of function on R. Okay, and then it has a very proper subspace, very nice subspace, that is called C-infinite function. So that means the function which are differentiable infinitely many times. Okay, it's called C-infinite functions. Okay, so these are infinitely many, infinitely many times, differentiable function. Differentiable function. Okay, so obviously this is a proper subspace because you can add to such function, it will be again independent function. If you multiply by a constant, still it is right. Now if you want to define a map, say as a simple map from C infinity to C infinity over R, so you send and function to derivative. These are not implied. So if all the polynomial functions are here, right? Sine function, cosine function, they are all here, right? They are infinite differential functions. So suppose you have this operator which sends f to the derivative, and then can you check what are the eigenvalues, eigenvector? So let us see. So for example, let there exists a C belongs to F, rather R, such that this T of F equal to C of F. But T of F by definition is F dash, right? So C of F. But what does that mean? This is kind of a system of differential equation, right? This ordinary differential equation, okay, or linear equation, order 1. So that you can write down the F dash by equal to C, and now if you solve it, then what happens? So logarithm of F will be constantly C into F. So what does that mean? That means that f of t is nothing but of the form some constant time e power ct, right? This is the solution of this equation, right? And now you see that this function is obviously infinitely differentiable, this element of C infinity. And not only that, if you just multiply by if you just take what is f of t, this is nothing but f dash t, which is nothing but c times k e power ct, which is nothing but c times f, right? So satisfy the equation. So what does that mean? That means for every real number c, so if whatever real number you choose, you have a eigenvector with respect to that, right? So this is so eigenvalues are yeah, so eigenvalues are C, and for with respect to C, the eigenvectors are what? So if of t are the eigenvectors, which are nothing but of the form some constant time e power ct. This is eigenvectors corresponding to the eigenvalue C, right? And obviously if you choose C equal to 0, still you see that this is constant. So constant functions means everything is ending to constant are the eigenvectors. Okay, So this is an example, nice example. Okay, so now recall that how do you define characteristics or eigenvalues for with respect to matrix? Because when you have finite dimensional vector space, then you know that every linear operator is nothing but a matrix, right? So you can fix any basis and you can define the matrix with respect to that basis, right? Then how to define it? So in that case, so let me define it. So let suppose we have a matrix. So let A is matrix, maybe n plus n matrix over the field, same field where vector space is defined. Then we define we define the eigen values of A by so this is T is already given to me, right? So T with respect to some basis. Okay, so no, I should say that otherwise. By eigenvalues by that of T in operator, right? What is T? So T is here the function which is LA. What is LA? So with respect to a matrix A, we can define like multiplication operator, right? So LA is what? So LA sends a vector V to AV, right? So this matrix is actually defined by this linear operator. Similarly, conversely, if you have a T inside LV, then you can define the eigenvalues of this is by so eigenvalues of T, they are actually this said same as the eigenvalues of that T with respect to some basis. So you fix the basis first and then you find out. So they are same actually. So it doesn't matter whether you choose a matrix first and then coming to eigenvalue, you can use that definition, or from the linear operator you can go to eigenvalues the matrix and then you can do it. What is the advantage here? That I'm going to tell you the advantage here. So now we are going to give some equivalent condition of eigenvectors and eigenvalues for finite dimensional vector space. So what happened for finite vector space? For finite vector space, we know that. Okay, so let me assume that so let dimension of V is finite, and you have a linear operator on V, so element of LV. Okay, so then and obviously I'm assuming an scalar, say. Okay, then the following are equivalent. Following are equivalent. What are the following? So number one is that C is an eigenvalue of T. Number two is that the operator, so you start with the operator T minus C of I. So this operator is not invertible. So this is also linear operator, right? So the question is whether it's in isomorphism or not. So it's not invertible. Okay. Invertible. Okay. So these are also called singular. Singular means it is not invertible. And obviously the third is very straightforward from 2 that it is not invertible means what? That means the determinant of this operator. So when I am saying determinant, I mean the determinant of the matrix corresponding to this operator with respect to any basis. Okay. So that this determinant must be 0, and that is obvious. 2 plus is obvious, right? So no, it's not invertible means that there must be 2 rows or 2 columns repeating, right? And hence determinant is 0. And yeah, so then how do you do 1 plus 2? So 1 plus 2 is obvious also. So if it is eigenvalues with respect to some eigenvectors, so like let's say V be the eigenvalue, it's an eigenvector corresponding to C, and then what happened? Then obviously you know that first of all V not equal to 0 and TV equal to CV, okay, and that implies that T minus Ci of V equal to 0, right? So what does that mean? That means V is actually surrounding vectors such that T minus Ci of V equal to 0, so this implies V belongs to the null space of that operator, right? Or the kernel or whatever. So what does that mean? That means that the null space of T minus Ci is non-empty. It's non-trivial. It's not equal to 0. So 0 is always there, but you have an non-zero vector also. And that already proved that this is equivalent to saying that null space is more than one element means that T minus Vi is not 1, right? That is not injective, right? If it is not injective, then it cannot be invertible, right? Because invertible means 1 onto both. So thus T is not invertible. Not invertible. That means T is singular. Okay, T is singular. And this is 1 plus 2. 2 plus 3 is also very simple because the moment T is not invertible means it's not. This is what should I say? This is singular. Then that implies the determinant is 0 because so what is that? What is the meaning of the operator is singular? If determinant is non-zero means what? Determinant non-zero means that the corresponding linear operator is actually both 1 and 2. Right? I mean, 1 is enough, right? Because 5 dimensional. So whenever you want to find the vector space, and 1 means onto on LV. Okay. So this is a simple observation. Okay. Now question is that okay. So now obviously you can define something called characteristics polynomial. Okay. So let me write down characteristics polynomial. Polynomial for a matrix. Okay. So for any matrix A is element of Mn cross n means n cross matrix over F. So the characteristic polynomial is defined by the characteristic polynomial of A is defined by what? This is defined by this f of x or f of t, whatever, let f of x, that is xi minus a, determinant of that. So this is my symbol. This is main determinant. Okay, determinant of xi minus a. Obviously, so some people also use the other also. Some people use that this is determinant of a minus xi. Okay. But that is same, because the only problem will be there. It's not problem. Only thing is that it will be, there will be a sign problem, right? That the sign of x may be minus 1 to the power n, but that does not have any impact on the eigenvalues of that, right? So and obviously the way we defined, okay, yeah. So this is the definition for characteristic polynomial for A. Now question is that corresponding to every matrix we have a linear operator, right? And obviously vice versa for so what is the connection from A you can go to LA, right? Similarly, for any matrix, any linear operator T, you can go to TB. That is with respect to some basis. Okay. My question is that if I define by these, then can I define the same definition from characteristic polynomial for T? For example, if you start with the linear operator T, can I define that characteristic polynomial linear operator by this kind of like this determinant of that TB? Instead of A, I write down T x minus A with respect to the basis B. Because that matrix depends on the basis B, right? So that's a question to ask. The answer to this question is that yes, we can define. And why you can do it? Because of this. So we know that when you change the basis, one basis to another basis, then corresponding the change of basis matrix are similar matrices, right? We proved in last lecture probably. So when you have two similar matrices, they actually have the same characteristic polynomial. So it doesn't matter whether you can write down with respect to which basis. Okay, whatever basis you choose, the characteristic polynomial will be always same, right? So let me just prove this. So this thing that characteristics polynomials of the similar matrices are same. So it doesn't matter which basis you choose, the corresponding to a different basis, the matrix will be similar. And if you know this theorem that characteristic polynomial are actually same for similar matrices, then we are done, right? Then you can define by the same method. Now how do you prove these things? So let me assume that, let me assume that you have two matrices, A and B. A and B are two similar matrices. Okay. Now you need to prove that they have the same characteristic polynomial. Now similar means what? That means there exists some non-singular matrix, right? So there exists a non-singular matrix. It means determinant not equal to 0. Okay, that is the meaning of non-singular. Singular means determinant equal to 0. Non-singular matrix. You can say that a change of basis matrix, right? Say P belongs to M n cross n of A, such that what happened? Such that this is a B equal to, you can write down P inverse AP, right? This is by definition of similar matrices. And now if we know the characteristic polynomial A, then can you find the characteristic polynomial B or not? The answer is yes. Why? Because this means that if you choose determinant of B, that would be nothing but the determinant of P inverse AP, right? This is the meaning. And hence, if this is true, then you can write down similarly that okay, so thus determinant of say xi minus b, which is a characteristic polynomial of the matrix B, you can write down this as determinant of xi, and b is nothing but p inverse ap, so you just substitute the value xi minus p inverse ap, right? But I is the identity matrix which commutes with every matrix, right? So you can multiply by p inverse and p, so you can write it down determinant of x into this p inverse ip. So p inverse equal identity, and I is commutes with every matrix, so there is no problem. So we can write down that this, and hence this is nothing but determinant of, now we have p, take p inverse common here, then x minus I, and then a, and then p. So you multiply p inverse from left side, p from right side, so this two are same, right? But this is nothing but product of three matrices, and you know the determinant of the product of the matrices is nothing but the product of the determinant of the matrices, right? So this will be determinant of p inverse, the determinant of xi minus a into determinant of p, right? But determinant of p inverse is nothing but 1 by determinant of p, so that this will get cancelled, this one get cancelled, and you will have a determinant of xi minus a. See, determinant of xi minus b is nothing but determinant of xi minus a. So that means what? That means they have the same characteristic polynomial, right? So this is the proof. So when you have a characteristic polynomial over two similar matrices, they must be same, right? Now with the help of these theorem, we can define it in definition that the characteristics is polynomial of let's say t belongs to linear operator t belongs to LV is defined as the characteristic polynomial of that the matrix representation of t with respect to any basis, because we know that it doesn't matter which basis you are choosing, right? So note that the characteristic polynomial, no matter which way you define determinant of xi minus t, or the other way, determinant of, I mean, no matter what way you define, doesn't matter. Okay, there will be only change of sign, right? Determinant of t minus xi. Whatever the way you define it, and then you stick it. Okay. So, but the thing is that the operator t always satisfies that polynomial. That means t of determinant of, so for example, this is my definition, and then this is t minus t, so which is 0. So what does that mean? That means that the linear operator or the matrix, they always satisfy the characteristic polynomial. Okay. So what does that mean? So that means that the solution of this okay, okay, and also, so that means determinant of this 0 means what? Determinant of this 0 means from our previous theorems. Okay. Yeah. So this is 0 means that C must be eigenvalue. So this is a way to find out the eigenvalue. So how to find out the eigenvalue of a linear operator or a matrix? You find out the determinant first, determinant of x minus a, and then find out, so that will be a polynomial, and then find out the roots of the polynomial, and those roots will be the eigenvalues, right? So eigenvalues are nothing but the, thus eigenvalues are the roots of the characteristic polynomial, right? Characteristic polynomial. Okay. Now let us do some example where we can even give example of eigenvalues and everything. So maybe you can start with some known examples. So maybe one example. So let me start T on R2. So R2 is 2 cos 2. So R2 is this plane, right, over R, and so LR2 is nothing but the space of linear maps on R2, and then you take T belongs to LR2. Okay, and so they will be of the form 2 cos 2 matrices, right? So let me write down the matrix forms of T, which is maybe say 0, -1, 1, 0. Okay, so this is, you can, as per I discussed earlier, this is kind of rotation matrix. You remember rotation matrix is equal to angle 90 degree, right? Now over R2, what happened? Over R2 over R. Okay, so over this, what happened? So if you want to find out the characteristic polynomial, say fx, so what will be the fx? Fx will be determinant of xi minus a, and what is that? That is, so let me define the matrix first. So xi is at what? X identity matrix, right? So 2 cos 2 identity matrix is what? 0, 0, 0, and a is 0, -1, 1, 0, the determinant, and this is x -1, -1 plus 1, then -1, and x. And what is the determinant? So this is x square plus 1. Okay, yeah. So this is the characteristic polynomial of A, right, over R, and obviously it has no roots, right? So thus A has no eigenvalue, no eigenvalues over R. But if you do it over C, so if you take, this is C square over C, but over C means you consider the polynomial over C means what? So you start with C2 over C, and in this case, what happens? In this case, it has eigenvalues, right? In this case, you can write down that if it is nothing but x plus that plus iota and minus iota, right? So in that case, plus I and minus I are the they are the eigenvalue of that same polynomial, right? Okay, so characteristic polynomial is this over R over C this, and now you see that for underlying field, if we change that existing characteristic polynomial, eigenvalues may be also changed, right? Okay, this is one simple example, and maybe you can give some more interesting example. Yeah, I think we can find out this is okay. Okay, so the question is that can I find out the eigenvectors also? So maybe I can give one example to find out the eigenvectors also. So let me start with the matrix, say A equal to 1, 1, 4, 1. So this is the matrix for some linear transformation, right? And obviously you can find out eigenvalues first. So what are the eigenvalues here? So eigenvalues will be again, you first find out the characteristic polynomial, so that will be determinant of x minus 1, and I'm sorry, x minus 1, and then minus 4, x minus 1, right? So what does that mean? That means x minus 1 whole square and minus 4, right? So this is what this is, x minus 1 plus 2 x minus 1 minus 2. A square minus b square, a plus b minus b, right? So that means this is x plus 1 and x minus 3, right? And hence the characteristics values or eigenvalues are minus 1 and 3 are eigenvalues of A, right? This is okay. We have two eigenvalues. Now we need to find out eigenvectors. So what are the eigenvectors corresponding to, so for example, 3 or minus 1. So let me start with 3. So now to find out eigen vectors corresponding to the eigen value 3, we start with what? So we start with this, that is, so we know that any eigenvalue will be of the form AV equal to CV, right? So A is the matrix this, and suppose this is V1 V2, because this is two-dimensional vector space, right? R2 over R, and this has to be of the form 3 times V1 V2, where V equal to V1 V2, obviously it's non-zero, is an eigen vector of A, right? Now I need to solve this equation and find out what are the V1 V2 look like. Okay, how this V1 V2 look like. Now if you solve the equation from here, what you have? You have, so this V1 plus V2, and then 4V1 plus V2, that has to be equal to 3V1 3V2, right? So what does that mean? So what is the equation? The equation you are getting, the equation number 1, V1 plus V2 equal to 3V1, and equation number 2 is what? 4V1 plus V2 equal to 3V2. Okay, 4V1 plus V2 equal to 3V2. Now if we just subtract directly, then what happens? Then if you subtract it, we'll have minus 3V1 equal to 3 times V1 minus V2, right? Okay, I think we can write down a little bit more. Before subtracting, you can actually more simplify it. How? We can write it down everything together. Okay, so let us write it down here. This is 2V1 minus V2 equal to 0, and here it is 4V1 minus 2V2 equal to 0, right? So either you can write down this or that. Okay, so what does that mean? That means so this means that, so this is actually, see, if you multiply the first equation by 2, you will have this equation, right? So this is actually give you the same equation, minus V2 equal to 0. So from both the equation, what we will have? We will have V2 will be equal to twice of V1. So thus the eigenvector will be of the form, the eigenvector vectors are of the form this V1, and for V2 to V1, right? And such that this V1 not equal to 0. So this will be the eigenvectors of this form. Now so what does that mean? That means so this is clear. They also, okay, so maybe I should say that if you collect the eigenvector corresponding to a whatever the eigenvalue you choose, they actually forms a subspace. You can, this is a simple observation. Okay, so let me first let me write down, then I will give that thing. For -1, what happened? Now for say c equal to -1 was another lambda, another eigenvalue. You can do the same thing. You can do 1 1 4 1 and v1 v2, that has to equal to -1 times v1 v2, and so this will gives you v1 plus v2 4v1 plus v2, that has to equal to -v1 minus v2. Okay, and this will give you the equation 2v1 plus v2 equal to 0, and from this 4v1 plus 2v2 equal to 0, so that is also same as 2v1 plus v2 equal to 0, and hence you can write down that v2 equal to -2v1, right? And hence for eigenvalue -1, eigenvectors are, so the eigenvectors corresponds to the eigenvalue -1 are what? They are of this form, right? So v2 minus v1. Okay, so that means v1 minus v1 such that v1 not equal to 0. Okay, now whatever the eigenvalue you choose, the eigenvector corresponding to the eigenvalue always forms a subspace. Okay, and they are called so definition: the eigenvectors corresponds. Okay, so I should not say eigenvector including 0, because 0 is not eigenvector. So I should say like this. I should say that plus 0 also need to put, right? So I should say that yeah. So this. So let me write down that E of C is the eigenvalue, and this is defined by all the V such that that your TV equal to CV. Then obviously C is what? So C is actually union of 0 is there, and the eigenvectors of C, right? Eigenvectors corresponding to C. Okay. Now this space is, this is a claim. This is a simple claim that ECs are for any C subspace of V, and they are called the eigenspace. Eigenspace corresponding to eigenspace of C. Okay. Now why this? So how to prove this subspace? That is obvious, because 0 is already there, and if we add two eigenvectors, that is going to be again eigenvector, right? You multiply a constant, that will be again eigenvector, right? It's simple. So they will form a subspace. And similarly, in our previous example, now we see that so this is a subspace with respect to -1, so E -1, and you see that this is generated by the single vectors 1 minus 2. You can write down everything by v1 into 1 minus 2. Similarly, for E, this was where the other one, so this was your E3, and it is also generated by a single vectors. And that vector, so that vector is what? That vector is 1 2. Okay, now you see that you have two eigenspaces, and both are one dimensional, generated by single element, right? And has to be, because the whole space is two dimensional. So, and obviously Okay, maybe that thing I will discuss in my next lectures on the connection of this distinguishing eigenvectors or linearly independent of the vectors. Okay, that I am going to define the next class. Okay, so with the help of this, maybe I will stop my lecture here today.